In this example, you will analyze an electrokinetic sample injector that is commonly found to transport well-defined sample volumes of dissociated acids and salts. The model is made up of two channels, the horizontal focusing channel and the vertical injection channel. The two stages within the model are the focusing and the injection stages. During the focusing stage, shown in the previous video, pressure-driven flows are used to produce a focus concentration profile at the junction between the vertical and horizontal channels. Pressure-driven flows also inject buffering solution into the horizontal channels from both the upper and lower vertical channels. Once the system reaches a steady state, the device switches into the injection stage, which will be analyzed in this video. In this stage, the pressure-driven flow is turned off, and an applied electric field drives the ionic species from the focusing zone into the vertical injection channel. Two modes of operation are demonstrated, Mode A and Mode B, which differ only by the electric field boundary conditions. We will compare both modes and analyze the concentration profile resulting from these different electric boundary conditions. To begin the injection stage, add a study and select stationary as the study type. Click back into the convection, diffusion, and migration node and make the velocity field user-defined. This will turn off the induced creeping flow by setting all velocity directions to 0. Right-click Transport of Diluted Species and add a flux to the four end boundaries as seen. Enable the Species C checkbox, and in the N0 edit field, type in the following to define an outward normal electrophoretic flux. From the Electric Currents node, add an electric insulator. In the Graphics window, select boundaries 1 and 54. From the same node, add an electric potential of 0 volts to boundary 21. Add another electric potential boundary, but this time, change the electric potential to negative 3.2 volts, then select boundary 26. This will ensure that the charge will only flow in the direction of the injection channel. We'll define a time-dependent study step to visualize the sample flow into the injection channel at different times. However, in order to decrease computational cost, we will define the electric potential as a stationary study considering it does not vary as a function of time. To do so, under Study 2, click Step 1 Stationary and uncheck all but the electric potential. Now, add a time-dependent study step by right-clicking on Study 2 and choosing Time Dependent. In the Times Edit field, define a range from 0 to 0.6 seconds with an interval of 0.06, which will compute a total of 11 solutions. Under the Physics and Variables section, uncheck the Electric Currents and Creeping Flow Physics. Right-click on Study 2 to show Default Solver. Expand the Solver 4 node and click on Dependent Variables 1. From the Defined by Study step list, choose User Defined. In the Initial Values of Variables Solved For section, choose Solutions from the Methods list and Solver 1 from the Solutions list. Enter the same parameters for the Initial Values Not Solved For section. These steps will allow the solver to use the solutions from the focusing stage as the initial condition. Right-click on Study 2 to compute the model. A second concentration node, Concentration 1, is created. In it, choose Solution 4 as the dataset, which at time 0 should be identical to the focusing solution obtained earlier. To better dynamically visualize the time-dependent solution, let's create a player by clicking on the Player button on the toolbar. Here, you can see the effects of the electric potential on the separation of the sample, but it is difficult to tell the concentration profile through the injection channel. Let us define a line in the middle of the injection channel and plot the concentration along that line. This will allow us to better understand the concentration versus distance as a function of the study time. Under Results, right-click Datasets and choose Cutline 3D. Choose Solution 4 as a dataset and enter the values shown in the Line Data section. Plot the cut line to verify that the line looks similar to the one displayed here. From the Results node, add a 1D plot group and use the cutline dataset. Right-click 1D plot group 9 and add a line graph. Click Replace Expression and choose Concentration. Under the X-axis data section, change the parameter to expression. Enter the expression shown as the length of the cut line we defined in the Dataset section. Then plot the graph. Here you can see the concentration versus distance along the injection channel as a function of time in mode A. The separation is not perfect as it leaves a rather non-uniform sample profile over time. This will be improved upon in mode B. Now let's similarly analyze mode B and compare it to mode A by changing the corresponding boundary conditions. Go into the Electric Potential 2 node and change the boundaries to 21 and 54. Here we define the injection channel outlet as well as the focusing channel outlet as 0 volts. Add another electric potential to the Electric Currents node, select boundary 1, and enter -1 volts as the electric potential. This will override the previous insulation boundary we created and will make the sample inlet boundary also have a charge of -1 volts. Therefore, an outward flow will develop in the sample inlet as a result of the potential difference of 2.2 volts between the top buffer inlet boundary and the sample inlet boundary. Under Study 2, Solver Configurations, right-click on Solver 4 and disable it to keep the solutions for Mode A. To add a replacement solver for Mode B, right-click Study 2 and Show Default Solver. In the Solver 6 node, go into Dependent Variables 1 and change the Define by Study step to User Defined. Now under the Initial Values of Variables Solved For section, change the method to Solution and from the Solutions list, choose Solver 1. Similarly, change the same parameters in the Initial Values of Variables Not Solved For section. Again, this will refer to the solutions from the focusing stage as an initial condition. Right-click Solver 6 and compute the model for the last time. On the results, click Concentration 5. Create another player by clicking on the Play button. During Mode B, you can see the backwards movement of the sample in the sample channel. However, it is difficult to tell the concentration distribution throughout the injection channel. As a result, we will create another 1D plot group to visualize the concentration. On the dataset, right-click on Cutline 3D and choose Duplicate. Then change the dataset to Solution 6. Add another 1D plot group and choose Cutline 3D 2 as the dataset. Add a line graph and under the Y-axis data, click Replace Expression. Choose Transport of Diluted Species, Species C, then Concentration. Under the X-axis data section, change the parameter to Expression and type in the following expression. Plot the graph to view the concentration in Mode B. Finally, we can plot both graphs in two separate windows and put them side by side to visualize the difference in the concentration profile. From these graphs, we can conclude that Mode B provides a cleaner and more uniform separation of the sample. As you can see from the graph, Mode B contains a more bell-shaped curve indicating an even distribution of the sample that will be ready for further analysis. For more information about this model, visit komsol.com/electrokinetic-valve.